Unit 5 is based on EMF and Faraday's law. So in this unit, we'll talk about how the change in magnetic field intensity linked with a conductor induces EMF or current in that conductor. Okay, we'll talk about electromagnetic induction. We'll talk about magnetic flux. And there are other topics as well, motors, generators that we're going to discuss in this chapter, in this unit, overall unit, right? So the EMF, you know the meaning, the full form of the word EMF, this abbreviation.
Electromotive force
Is this
or
any kind of
voltage.
force or what is it?
It is voltage, like
It is voltage.
equal to voltage.
Yes, EMF is voltage. And how do we define it? What is electromotive force basically? See, there are three terms in this word. One is electro, second is motive, and third is force. So what do you understand by this term when you just divide it into parts? Then what will you want? What do you get? What do you understand just by dividing it in parts? So there is some kind of, what is it?
There is force because of electricity moving or
Electro, the word electro, where we find word electro, it means charge, right?
charge
Motive
moving.
is some kind of push, we can say, or motive or motion, and this is force, right? So there is some kind of force that allow the charges to move, that allows the charges to move. Because of that, charges can move easily. So EMF is something like this, I guess. What do you think? So electromotive force is basically, if we take an example of water tank and electric motor. So if this is the water tank placed at certain height, then we have to switch on the motor to fill the tank, right? Because water does not go itself at a certain height. But we can get water from the tank very easily in our taps. So to move the water in upward direction to the water tank, we need an external agency like electric motor. We switch on the motor for this, but to move the water in the downward direction, no need of any kind of motor, right? It is not needed at all. Water goes down by itself because of the gravity, we can say. Same thing happens in case of charges. So charges can easily flow from an object at higher potential to an object at lower potential. So if an object is at higher potential and we have some other object at lower potential, so charge can easily flow from higher to lower potential. But what if I want to move the charge from lower to higher potential? Then again, we need something like motor, as in case of water, we need it, right? So there is a kind of motor is needed and which makes the charge move. And because of this, charge can easily flow from lower to higher potential, irrespective of this, that the fact that this part is at lower and this part is at higher potential. It goes from lower potential to higher potential quite easily. So that motor is EMF here in this case, and it allows the charge to move from lower to higher potential. Charge can easily flow like this if there is some kind of motor or agency is there which moves the charge or pushes the charge to move from lower to higher. So that's electromotive force. And in this chapter, we're going to talk about Faraday's law as well. Faraday's are based on electromagnetic induction that we're going to discuss. So electromagnetic induction is another term here. Let's write the full form: electromagnetic induction. So what do you understand by this term? Electro, again, the meaning is charge or current. Magnetic, it is related to magnet. And induction means something is induced. No? Now, how will you define EMI?
What does induce mean?
Induced is, we can say, produced.
So current is produced.
So we change the magnetic field and current is produced, even if there is no source of, potential difference or battery or any cell or anything. Okay. So in this case, if we have a conductor or something, if I have a conductor and it is placed in a magnetic field like this, please look at the screen. So this conductor or ring, whatever it is placed in the external magnetic field, then no current will be induced in the conductor. But once the we move the conductor or the magnet, if there is a relative motion between the conductor and the magnets, then current can be induced in the conductor. And you can see that there is no battery connected with the conductor, nothing else is there. It is just a wire which is placed there in the magnetic field. So how do we induce current or induce EMF in any conductor which is placed in the magnetic field? By changing it. We can induce it by changing the magnetic field or the orientation of the conductor, or we can change the area of the conductor linked with the magnetic field, whatever. We'll discuss about it. Okay. So electromagnetic induction deals with this thing, that without a battery, without any external source of potential difference, how can we induce EMF or current in a conductor that is placed in the magnetic field? Okay. So we're going to discuss all these things in this chapter, and please take the screenshot. Number of field lines crossing an area is the flux. So electric flux is denoted by phi with a subscript E. This is electric flux. It is basically the number of field lines crossing, electric field lines crossing an area. And magnetic flux is phi with a subscript B. It is the number of magnetic field lines crossing an area. Okay. So suppose we have we have magnets, and there is a conductor placed in the magnetic field, external magnetic field. And because we know that magnetic field lines move from north to south pole, right? So this is the direction of magnetic field lines. And you can see the field lines crossing this conductor. So the number of field lines crossing the unit area of conductor, or crossing a conductor, crossing a given area, is called magnetic flux. So if there are more number of field lines crossing a given area, then there is more magnetic flux associated with the conductor, linked with the conductor. And if there are less field lines crossing the area, then there is less magnetic flux linked with the conductor. Okay. And how do we define it? We write magnetic flux as phi B, and it is the dot product of magnetic field intensity and area vector. Now, what is this area vector? We need to understand. See, first of all, this is a scalar product. And when we take a scalar product, we get a scalar quantity. Scalar product means in vectors, we have two types of product. One is dot or scalar product, and other is cross or vector product. So when we take the cross product, we get a vector quantity in vector product. And if we take the dot product, then we get a scalar quantity. So magnetic field intensity is a vector quantity, right? This we know, no? Magnetic field intensity is a vector quantity. It has direction north to south. And this area vector is also a vector quantity. But when we take the scalar product of these two vectors, we get a scalar quantity. So magnetic flux is just, because it is just the number of field lines crossing an area. So it is a scalar quantity. Okay. And how do we write it? We write magnetic flux as either by this vector B dot A, or we can write BA cos theta. Because when we take the scalar product, we write cos theta. Cos theta is the angle between the magnetic field intensity vector and area vector. Now, how do we find the direction of this area vector? So area vector is basically, suppose we consider a surface, okay, and it has an area A. This surface has area A. Then area vector, because we're talking about area vector here, right? So area vector means which has area, we consider the magnitude plus direction both. So area is, we can find area like this. We can find area of any loop or any, but whatever it is, we can find area. We know what area is. The space occupied is the area, right? And vector, because it is a vector quantity, so it has direction. Its direction is perpendicular to the plane of the area vector. So in any position we can draw a conductor. So if we have drawn a conductor like this, so this is the area, we can find the area, and the direction points perpendicular to the plane of the area. Direction always points perpendicular to the plane of the area. So this is area vector. Okay, so in this particular case, if we talk about area vector and magnetic field intensity, the direction of magnetic field intensity is from north to south. And what is the direction of area vector? Perpendicular to the plane of the coil, no? If this is the coil, then perpendicular to the plane of the coil is the area vector, no? So both, you can see magnetic field intensity and area vector, they are pointing in the same direction. So what is the angle between magnetic field intensity and area vector in this case?
It would be same.
So angle is 0 degree, no? Because both are pointing in the same direction. So we can write phi B, the magnetic flux, as BA cos 0 degree. And what is the value of cos 0 degree? 1. So this is the maximum magnetic flux, or we can say maximum number of field lines that can cross through a conductor situation. So when we place a conductor perpendicular to the external magnetic field, then maximum number of field lines can cross through it, can pass through it, and flux is maximum. Flux linked with the coil is maximum in this case, because maximum number of field lines can cross the coil in this particular situation. Clear?
So it will be maximum when the field lines, no, the magnetic field and the area would be in same direction.
Yes, when area vector and magnetic field intensity point in the same direction, when we place the coil perpendicular to the magnetic field, then maximum number of field lines can cross.
Okay.
Okay. And this we have discussed already, this magnetic flux is a scalar quantity. Now, what do you know about the unit of magnetic flux? What is the unit? Any idea?
Is WB.
It's Weber. And how do we write it? We write capital W and small b for Weber. And what is the unit of magnetic field intensity?
Tesla
It's Tesla. And for area,
meter
meter
square.
square. So we can say 1 Weber is 1 Tesla meter square. We can write like this as well. No? Should I clear the screen?
I don't get the perpendicular part.
Okay, I'll explain this to you again. See, if we have an external magnetic field, then how the field lines, pass? How do we draw the field lines for this kind of situation?
From north to south.
We draw the field lines like this, north to south. Okay. And if we have a coil and we have placed the coil like this, perpendicular to the magnetic field, then maximum number of field lines can pass through it. Right? Second situation is, again, I'm taking the same external magnetic field. And again, we'll draw the arrows. Arrows represents the direction of magnetic field intensity from north to south, right? But this time I'm going to place the coil horizontally, not in vertical position. Now you tell me how many field lines are crossing this coil.
No field lines are crossing.
No field line is crossing the. So magnetic flux, what is magnetic flux? What is magnetic flux?
Number of field lines crossing a unit area.
Yes, number of field lines crossing an area, right? So in this case, in the first case, maximum number of field lines are crossing the coil. But in the second case, we have seen that no field line is crossing the coil. So magnetic flux linked with the coil is maximum in the case where the coil is placed perpendicularly in the field lines. You can see it is placed perpendicular. It is making an angle of 90 degree with this. Coil is making an angle of 90 degree with the field lines, no? It is placed like this and field lines are going like this. So when the coil is placed perpendicularly, then maximum field lines can cross through it. So 5B is maximum. But in the second situation, when the coil was placed horizontally, then you can see no field lines are crossing the coil and magnetic flux is minimum or zero, we can say. Mathematically, it is zero and theoretically, it is zero and practically, it is minimum. Clear? Now we can prove it mathematically. And how will we prove it? See, in the first case, if I draw the direction, if I mark the direction of both the magnetic field intensity and the area vector, then magnetic field intensity is pointing in this direction, north to south. And area vector, how do we draw the direction of area vector? We draw the direction of area vector always perpendicular to the area, right? This is how we draw the direction. And for this particular coil, if I draw the direction, how will I draw? Perpendicular to the plane of the coil. So this is the direction of area vector, right? So if I write magnetic flux, we know that it is the scalar product of these two vectors, magnetic field intensity and area vector. So we can write this as BA cos theta. So this theta is actually the angle between magnetic field intensity and area vector. Okay. So what is the angle between B and A in this particular situation?
0 degree.
Yes, theta is 0 degree in this case and cos 0 degree is 1.
1.
So phi B would be VA. So this is the maximum magnetic flux that can, cross or that is associated with a coil. So when the coil is placed perpendicular to the field, then it has maximum magnetic flux. Maximum number of field lines can cross the coil. But what if we place the coil horizontally like this? Now in this particular situation, again we will write the same formula. But now what is the angle between vector B and A? Let's find out. So the direction of magnetic field intensity is from north to south. And what is the direction of area vector in this case?
Perpendicular. So,
Perpendicular to the plane like this. Direction of area vector is perpendicular to the plane. So what is the angle between these two quantities, B and A?
90.
This time angle is 90 degree. Because magnetic field is going in this direction, area vector is going in upward direction. So angle is 90 degree. Cos 90 degree is 0.
Um,
It's 0, right? So magnetic flux is BA cos 90 degree, hence it is 0. So minimum magnetic flux. Phi B, the magnetic flux is 0 in this case, right? This is the minimum value. So when the coil is placed horizontally, parallel to the magnetic field. So when the coil is placed parallel to the magnetic field, magnetic flux linked with the coil is 0. And when the coil is placed perpendicular to the magnetic field, then magnetic flux linked with the coil is maximum. I hope this part is clear.
yes.
Okay, let's take another situation. Again, we are going to draw the field lines first. External magnetic field we are considering. But this time I'm going to place the coil at an angle with the magnet. It is making an angle with the magnetic field tensor. It is placed like this, obliquely placed like this. Okay. So in this particular situation, again, we will mark the directions first. So this is the direction of magnetic field from north to south. And how will we draw the direction of area vector? Perpendicular to the coil?
Perpendicular
Yes, it is
within
perpendicular
45
to the
degrees.
coil. Like this. Now you can see the angle between these two. What is the angle? Let's elongate this, stretch this. So backward अगर हम extend करते हैं, let's extend the vectors in the backward direction, you will get this angle. So this is the angle between B and A, right? It's making an angle. So this time phi B is BA cos theta. So theta is neither 0 degree nor 90 degree. So from, if you take, it is any angle between 0 and 90. So theta is greater than 0 degree and less than 90 degree. So any value between 0 and 90 is the value which is neither maximum nor minimum, right? Because at cos 0 degree we get the maximum value 1. At cos 90 degree we get the minimum value 0. But if we take any angle between these two angles, then we get the value which is neither maximum nor minimum, right? So lines will cross the coil, but comparatively fewer lines will cross. Some magnetic field lines will not cross the coil. Okay? So less than maximum value we can say. It has less than maximum value. Maximum value is BA and this is less than maximum value. Clear?
Okay.
Please write this. This is your chapter 5. So in this chapter, we are going to talk about this. Magnetic flux we have already discussed. You can see the perpendicular sign there with B. So what does this perpendicular sign indicate? Hmm?
At the conductor, no, the area is perpendicular.
It indicates that the conductor
Magnetic
is
field.
placed vertically in the magnetic field. The lines are crossing
Okay.
the conductor perpendicularly. So this we have discussed already. Magnetic flux we've done from the slides, right? So here we have situations, different situations where we place the, this we have done, right? So in which case out of these two, figure 1, there are two, figure 1A and figure 1B, we have two different figures here. So in which case magnetic field lines, crossing the conductor is greater?
A,
A. So which has greater flux?
A,
A has greater flux, yes. Now we have a situation here where we have a coil and we have placed the coil, you can see we have an external magnetic field and now we are moving the coil towards the magnets and this is what we have different positions where we have placed the coil. So at position W, is the coil in the magnetic field?
no, it's
It is not
outside.
it is outside the, so no field lines will cross through it. So magnetic flux linked with the coil in this particular situation is
0.
0. And when we move the coil slightly towards the external magnetic field, now you can see in position X. Position X is when just the coil just entered the external magnetic field, then field lines passing through the coil will increase. So magnetic flux is increasing.
So it's maximum.
No, it is not maximum. It is maximum at position Y. When the coil goes from position X to position Y, then flux that is, linked with the coil is maximum. Number of field lines that crosses the coil would be maximum in the case when the coil passes, from position X to position Y. And at position Y, it reaches its maximum. And after position Y, again, the coil is moving towards position Z. So in position Z, again, we can see that the field lines are decreasing and it becomes zero, no, after it reaches the position Z. So magnetic flux again is zero. So if I ask you to draw for different positions, magnetic flux versus different positions graph, so how will you draw it? And because we are assuming that this coil is moving with uniform velocity, it is moving with constant velocity in the magnetic field. So flux will increase steadily. Flux will increase in a, equal amount of flux will increase in equal intervals of time because velocity, the speed is constant with which the coil is moving. So flux will also increase the same way, right?
Okay.
So how will we draw the graph? So you can see we have already one graph here. We can discuss. So at position W, flux linked with the coil was zero. No, here the flux was zero at this position. And when it reaches at Z position, again the flux becomes zero because coil was outside the external magnetic field. But when it goes from W to X, it because the coil is going into the magnetic field, external magnetic field, so flux increases, right? So that's why we have drawn the graph like this. So in this particular situation, we can see flux is increasing. And when it reaches X and from X to Y, it goes to Y, then because it is in the magnetic field, it stays in the magnetic field there. So here the flux is constant. There is no change in the magnetic flux because it is the whole coil is there in the external magnetic field. But after it reaches Y and goes to Z, in this particular situation, again the coil is moving away from the external magnetic field. So flux linked with the coil will change. And this time it is decreasing because it has reached the maximum value here. Now it is decreasing. So less field lines will cross through it. So this is how we can draw the field line, flux curve graph with the different positions. And same, see, when we'll do Faraday's law of electromagnetic induction, we'll redraw the graph with, induced EMF, and you might have done in school. See, there are four ways to change the magnetic flux through the loop. How can we change the magnetic flux linked with the conductor? So if we have an external magnetic field and a coil is placed in the magnetic field, then field lines will cross through it, will pass through it. Now the question is, how do we change or how can we change the magnetic flux linked with the loop? First is by changing the strength of the magnetic field. Because if we have a, weak magnetic field, then fewer lines will be there. Because field lines, what are field lines? Field lines are the imaginary lines. And what do they tell us?
The direction of
Field lines tell us about the strength of magnetic field intensity at any point, right? So if we draw the field lines quite close together, or we draw the field lines at a little distance, so where is stronger magnetic field we have?
in first one.
Yes, in the first situation, magnetic field intensity is greater as compared to this, so stronger magnetic field. So field lines basically indicate the strength of magnetic field intensity at any point. So if we change the strength of magnetic field, then we can change the magnetic flux linked with the loop. है ना? Second, move the loop into or out of the field. If I move my loop up and down, even then I can change the magnetic field lines entering the coil. Second, change the area of the loop. What if we change the area of the loop? I take a bigger loop or smaller loop we can take. So by changing the area of the loop again, we can change the magnetic flux, or we can, move the coil up and down and change the area accordingly. This is the other way we can do it. Second and fourth is by rotating the loop inside the field. So if we rotate the loop inside the field, suppose I place the loop like this, or I can place my loop like this. So we are rotating the loop. We are moving the loop in circle or in rotation. Again, we can change the magnetic flux through the loop. Okay. So the first three methods, in the first three methods, magnetic flux traveling through the loop is in one direction. Which means magnetic flux will increase or decrease in the same direction. Suppose I am using a weaker magnetic field, then magnetic flux will decrease. If I am using a stronger magnetic field, then magnetic flux will increase accordingly, right? And if I move the move the loop into or out of the field, again the magnetic flux will change accordingly, either decreases or increases. But if we rotate the loop, then while rotating the loop, the field causes the magnetic flux to travel through the loop in both directions as it rotates. And therefore, it is important to consider the direction of the change in magnetic flux to accurately draw a magnetic flux versus time graph. So when we take the rotation, we have to be very cautious about that. How do we draw the graph? Magnetic flux versus time graph, because whatever you do, you are changing the magnetic flux ultimately. No? So we can draw magnetic flux versus time graph accordingly. How the magnetic flux is changing with time, right?
Okay.
Next, we have this loop orientation. You can see here. So we have placed the coil in different ways. So this is the first scenario where we have placed the coil perpendicular to the magnetic field. So here the maximum number of field lines will cross through the coil. So magnetic flux is at maximum and can be calculated using this formula. And this coil is placed perpendicular. So what is the angle between the magnetic field intensity and area vector in this case? This is the direction of magnetic field and area vector would be perpendicular to the plane of the coil, no? So both are pointing in the same direction. Theta is 0 degree, right? While in the second case, now we have placed the coil like this in the magnetic field, somewhere between parallel and perpendicular to the magnetic field. So in this particular situation, area linked with the magnetic field lines is decreased. You can see here how many lines were crossing: 1, 2, 3, 4, 5. But this time, if we calculate, only 3 lines are crossing the coil, right? Because area linked with the magnetic field is somewhat reduced, and so the magnetic flux is also changed. It is decreased. And again, if I ask you to mark the directions of magnetic field intensity and area vector, how will you do it? Magnetic field is pointing in the downward direction, and area vector, this is how we write, this is how we mark it. No, we draw the area vector direction. Magnetic field is in the downward direction, area vector is pointing in this direction. Then how will you find the angle? This is the direction of magnetic field and this is the direction of area vector. So the angle between these two is theta. So it's BA cos theta actually. And this calculation is not required in VCE physics. We are not going to discuss this thing where we are taking the angles, right? In VCE physics. The third case, what do we have here? You can see the coil is placed parallel to the magnetic field, right? This time. And we can see that there are no field lines passing through the loop. So magnetic flux is 0. We can see in the picture, in this figure. But we can also mark the directions. Magnetic field is pointing in the downward direction. And area vector, how do we draw it? Perpendicular to the plane of the area. And we can see the angle it is making with magnetic field intensity is 90 degrees this time. And how do we calculate flux? Mathematically, it is BA cos theta. So BA cos 90 degree. 0. So no magnetic flux is there. Okay. Now we have a question based on this. In this question, we have a loop and radius is given. So we can easily find the area of the loop, right? Radius is 0.25 meter and it is placed with its plane perpendicular to the direction of changing magnetic field. Magnetic field is changing and it is placed like this, perpendicular to the field. The magnetic field increases at a constant rate from 0.04 Tesla at t is equal to 0. So at t is equal to 0, we have magnetic field equal to B1, we can write it is 0.04 Tesla. and at T1 we can say T1, okay, and at T2 is equal to 1 second. After 1 second, the magnetic field intensity is changed, and now it is 0.1 Tesla. So this is how magnetic field is changing from 0.04 Tesla to 0.1 Tesla at after time T, we can say. So draw a magnetic flux versus time graph to show how the flux changes with time. So we have to draw phi versus T graph. So we'll find first the initial flux and then the final flux, right? So how do we find the initial flux? Initial flux is phi B1 we can write, or phi BI as it is written here. And it is the initial magnetic field intensity multiplied by area, right? And final magnetic flux is phi B2 or phi BF, F for final, is the final magnetic field intensity multiplied by area. Area remains the same, area is not changing at all. We are only changing the magnetic field intensity. We are not changing the area this time, because we can also change the magnetic flux by changing the magnetic field intensity. This we have discussed in the previous section, right? So first we need to find area here. How will we find the area? Because radius is given, it is 0.25 meter and it is a circular loop. So what is the area of the circular loop? We can use the area of circle formula, pi r square. Just put the values here and you'll get area. Okay. Now we just have to put the values here to get the corresponding magnetic flux intensities. In the first case, it is 0.04 Tesla. So we'll write 0.04 multiplied by area, 0.196. We'll get our answer in Weber because magnetic flux is measured in Weber. In the second case, again, B2 is 0.1 and area is 0.196. We can multiply to get the area. Again, we'll get our answer in Weber. So you can see in the initial magnetic flux, we are getting the magnetic flux of the order of 10 to the power minus 3. While in the final magnetic flux, we are getting the magnetic flux of the order of 10 to the power minus 2. No? So if you want to draw phi versus T graph, this magnetic flux versus time graph, then we need to take these, orders equal, same. And for this, we need to convert this 10 to the power minus 3 to 10 to the power minus 2. So we can write 7.84 as 0.784 in 10 to the power minus 2. Can we write like this? Because I just want to make the orders same so that we can locate the points easily. We can write like this.
Yes.
Right? Now we will just, plot the points for initial and final magnetic flux like this. So at t is equal to 0, this is time at t is equal to 0. At t is equal to 0, your magnetic flux is this 0.784 into 10 to the power minus 2. While at t is equal to 1 second, magnetic flux is 1.96 in 10 to the power minus 2 again. So we had taken 10 to the power minus 2 here. We're writing the scale like this. मतलब इसमें convenient हो जाएगा because we have kept this 10 to the power minus 2 aside and we have just written the numbers here, so that we can easily, locate the points instead of taking like this, no, Weber. It is actually in decimals, this is the value, but we have just kept this 10 to the power minus 2 here and we have just marked the numbers and we can locate the points. Yes. Now we have a coil in this question with an area 10 centimeter square. Area is in centimeter square in this case, right? So we can convert this into area into meter square first. How will we do the conversion?
We can divide it by 100 to the power of 2.
Yes, 10,000 we can say meter square. So you'll get 10 to the power minus 3, no? As the area. It is placed in a uniform magnetic field of strength this. So magnetic field is given. It is 0.03. We can drop this 0 Tesla. So that the plane of the coil is perpendicular to the field direction. Plane of the coil is perpendicular means we have placed the coil like this, perpendicular to the plane of the coil. Perpendicular to the field lines, no? We have placed the coil perpendicular to the field lines. So the magnetic flux through the loop is closest to. So in this case, maximum magnet field lines can cross through the coil. So we can just multiply these two quantities to get the magnetic flux because angle is 0 degree, right? Cos 0 degree is 1. So maximum number of field lines can cross through it. Simply take the product and you'll get your answer.
It's B 3 times 10 to the power of -5.
Yes. And the unit is Weber, right? So we can write like this 3 × 10⁻⁵ Weber. That's the correct answer. Okay, next question. A loop with an area of 1 meter square. Area is given. It is placed in a uniform magnetic field of strength 0.5 Tesla shown in figure. Which of the following statement is correct? See, it is slightly tilted. So this area vector is making certain angle with the magnetic field, right? So this time area vector is making certain angle with the magnetic field. So what is the correct option? There is no magnetic flux. No, this is wrong. There is magnetic flux.
Is
Hmm?
it C?
Sorry,
There
which
is some magnetic flux.
part?
Is it C?
Your voice is cracking.
Is it C part?
C part. Let me read this part. There is some magnetic flux through the loop and it can be calculated. See, we cannot calculate it using BA because it is less than BA. BA is the maximum magnetic flux that is linked with the coil, right?
So we can calculate it by BA cos theta.
Yes, we will calculate it by BA cos theta because it is placed slightly tilted in the magnetic field. So there is
Okay.
some magnetic flux through the loop. It can be calculated using this. We cannot calculate it. There is a maximum magnetic flux through the loop. No, it is not maximum. And we cannot calculate it like this. There is some magnetic flux through the loop, but it is less than BA. That's correct. B option. We have some magnetic flux linked with the coil and we can calculate it using B dot A because it is slightly tilted, no? So there is some magnetic flux, but it is not the maximum magnetic flux linked with the coil. It is less than maximum, and this value is the maximum value, right? So we have this value less than maximum, BA cos theta. So B option is the correct option. Yes. So student places a horizontal square coil of wire with sides of length 5 centimeter. So we have a square coil this time. And it is placed in a magnetic field. Side is given 5 centimeter. Magnetic field is given 0.1 Tesla. How much magnetic flux passes through the coil? Find the answer. Done it?
Yes.
Have you done it? We'll find the area first and then we just multiply these two quantities to get the magnetic flux, right? And there you can find the answer in milliweber. It's 2.5 10 power minus 4 Weber. We can write the answer in milliweber as well. 10 power minus 3 is milliweber. 1 milliweber is 10 power minus 3 Weber. Next question.
I got 8 times 10 to the power -5.
Second question. You done it?
Yes.
Let me read the question. A student places a horizontal square coil of wire with sides of length 4 centimeter this time. Magnetic field intensity. Again, the same question we have here. Length is 4 centimeter. And area is length side square. So 16 into 10 power minus 4 meter square is the area and magnetic field is 0.05 Tesla. So just multiply these two quantities. 0.05 into 16 into 10 power minus 4 with 100. 16 5s are 80 into 16 5s are 80 into 10 power minus 6 Weber. Are you getting the same answer?
I'm getting 8 times 10 to the power of -5.
That's correct.
Oh, yeah.
Next question. A student places a horizontal square coil of wire with sides of length 5 centimeter into a uniform magnetic field of 0.1 Tesla. The plane of the coil is parallel to the magnetic field. Then how much magnetic flux passes through the coil? Plane of the coil is parallel to the magnetic field. So we have a square coil, no? So we can draw like this for square coil. And its plane is parallel to the magnetic field. Then how much flux passes through the coil? Find the answer.
Um, is it zero?
Yes, it is zero. Though length is given, magnetic field is given, but answer is zero. Why the answer is zero? Because the plane is parallel to the magnetic field. So area vector, it will point in this direction perpendicular to it, right? Mathematically, we can prove like this, or we can say that no magnetic field lines will cross through this coil in this case. Done? Can you answer this question number 2, 3, 5?
Yeah. Question two is zero because it's